Today we're going to see this modeling difficulties and what we know as the derivative form of the differential equations when you have i's and c elements in derivative form. What do we do? What does it mean? Can we in a way physically know what it means and how to solve it? That's the topic of today's lecture. So let's take a look in here. We're going to talk, I'm going to do a little introduction, and then we're going to talk about how derivative causality occurs. What does it mean? Um, we will see what is the physical meaning of the elimination of derivative causality. We will see how we can combine dependent elements to solve it, how to introduce extra elements or parasitic elements to do it. What about CAMG and derivative form? Can we detect the derivative form by using the program? And can we actually find a solution for derivative form? We will see the differential form of the equations. Then we see the implicit Cauchy form of the equations and the state space form and derivative causality. Then we will look at the CAMG solution at the relation to the physical reality. And let's look at the solution for multi-elements in derivative form. So when you have several derivative forms. And finally, what's the implication of this in the Simulink area? Is there an implicit Cauchy form, an explicit system? How do we do it? Okay, I think the best thing to do, seems to me, is to put a system together that mechanical engineers are very familiar with and that we can actually see the modeling of this. And so you see you have in here a system that is very well known. You have this, let's see, get this. We have the system of a cam follower system, and you see there, this is the cam in here, and it has a cam follower device, and then it has this push rod that connects to the rocker arm. You know, some of these have hydraulic components inside, but for now, let's look at just the mechanical side. So this is the rocker arm that is going to, when the cam goes up, this will push up like this, and this thing will go down to either close or open this valve. So up and down and to close or open the valve. We have in here this set of springs that are trying to push it up to maintain it in the closed position. And this is the topper that actually has a gap so that when the time comes, it's pushed down and then the valve gets open. So on the right hand side, we have the model of the cam, obviously here you can see, and there's the tappet here. It's a mechanical one, the push rod, and then we have a connection to the rocker arm, and it's pivoted here, and so this would go up and down. As you could see, these acquired positions like this maybe, or it would the opposite, or like this. The point is that it will represent the rocking arm motion of this element in here. And in here you will see the valve. This is the valve over here, which corresponds to this valve. So that is the engineering model that we have come up with to idealize this model, and from that we will produce a bond graph model. This, I think that it be easier to understand if we could even draw this in the on the system itself, just for illustration purposes. We have on the right hand side the corresponding bond graph, but I think that we could follow the procedure and just for practice see how this was generated. We put a one junction for each distinct velocity, and this would be also an input here. You have a velocity over here, obviously, and we can put the 1 for to indicate the omega velocity over here, like that. And then we have another one over here, and then the one over here, see? And then we can have one right here as a reference. So step number 2 that we do is to connect the elements that see these velocities, and obviously this is going to be a 1, the SF element over here. This is has a velocity of t input in here. So that's okay. And then you have the mass over here, which would be an I element. You have the other I element over here like this. And on this one, you have an I element with value j, which would be the moment of inertia of the beam. And in here, you have also an I element like this. And of course, the SF over here. Actually, we need to put it the other way. And if we look at that as a reference, then yes, that's fine. As long as we have the causal mark the other way, we're fine. So we put the elements that show the distinct velocities, and now we create the relative velocities or the velocity differences using a zero junction. So if we go over here and we create the zero, so this would be b of the ground minus b, let's call it b minus x1 dot. So x1 dot is the motion like this, x1 dot, and you could put x2 dot, and here omega, right? This is omega, and this would be x3, let's say, like this. So and then we create that and attach the elements that see those relative velocities, which there is a C and an R element over here. We're going to do the same thing over here like this. This is the velocity difference. And then there is a C element and there is an R element like this. And in here you have a third set of the same type of element. You see, like this, where you have a C over here and an R over here, like this. Okay, and then in here you have a transformation from the velocity v sub a to omega. You know that v sub a is equal to omega times a, or that omega is 1 over a. So times the velocity here. So this is a transformer element in here, like that.
How can you tell?
Hmm?
How can you tell it's a transformer?
Because of this equation, see? That the velocity of v sub a is omega times a. And v sub b on this other side is omega times b. And so this is a transformer equation. So here we have a TF over here. And then in here between these two, we have the same situation where you have the velocity here, and then this would be a 1, and then you have a C and an R element. And in here you have a similar situation. In this case, since we are coming from here to here, the arrow would be down, C, and then you have the R element. And you can see the picture that I draw on the left-hand side in red is exactly the same one on the right-hand side, but the one on the left is drawn in such a way that the elements correspond to the physical locations, and you can actually identify the physical parameters of this with a physical system. And that's why it makes it easier for people to understand. So in here we will see if there's any question about this. No. Okay, so what I was trying to say is that it makes it easier to understand when there's a one-on-one correspondence to the physical system, which bond graphs offer that in all the systems, really. Except that if you have some subsystems, perhaps we need to make additional models. But I think by overall, I think one can relate to a one-on-one correspondence. Here we are going to name the values in more understandable terms, and each physical parameter is designated with a bone number. So C3 becomes the elastic deflection of the tappet. C7 becomes the elastic deflection of the push rod, and so on. The R elements are internal structural damping. I9 mass of the tappet, I18 mass of the push rod, I27 mass moment of inertia of the rocket arm, I33 mass of the valve, and the TFs 15, 16 and TF 21, 22 are the transformations between the velocity at the extreme of the bar and the center angular velocity. And then you have the SF35 would be the motion of the camp, and then just make sure that we notice that 1 over C is stiffness. Okay, very good. Now we are going to create a situation where we have a derivative form. And you see in here the difference between this and the original one is that in this example we had the in this example, we had considered this beam as a rotational element only. But on this one, we consider the beam as if it would be made of this and this other mass, and do not consider the rotational inertia, but rather those two beams. So this is a conceptual design change. And what does it do? You see over here, it forces us to, this corresponds to this. And this one over here, this I element, corresponds to this one. So when you assign the causal form, the causal marks, this one becomes in derivative causality. You see, this is the I element in integral form would be, if you have the I element in integral form, this would be like this. But the I element in derivative form is going to be like this, see? This is, we have learned from the very basic definitions of what the I element is. So, we have produced derivative form in here based exclusively on the interpretation of the model that instead of being one rotational arm is composed of two masses. And I think I'm going to concentrate on the physics of this, on the physical model on the left-hand side, because I would like you to focus when this mass moves, what does this other one do? If this mass on the left-hand side moves up, what does the other one do? If this one goes up, this one is going to go down. All right? It's very clear. So wouldn't we say, let's name this 1 and this name it 2. Isn't it fair to conclude, or you may say it's logical to conclude, that the motion of 2 depends on motion of 1? Okay, right? You know the phrase that we just wrote over there, motion of 2 depends on motion of 1. You know, in technical terms, we could say that the equation that controls the motion of 2 is dependent on the equation of motion of 1. It has no choice. If it's motion 1, the 2 follows. So isn't it true that in this case we could say, we, by interpreting the system the way we did, we introduce a dependent element which really should not be there. And the reason I'm saying it should not be there is because on the previous example, it wasn't there. The previous example had considered the rotational inertia of the bar as a one single element. And here we're considering two, but because specifically of what this lever does, you realize that the motion of the one on the left determines the motion on the one on the right. And that's what derivative causality does. That's the interpretation of derivative causality. You are saying this is the one in integral form. This controls the motion of this one. Therefore, this one is in derivative form. Okay? So that's the first thing that we have done here is to interpret this, yeah, in derivative form. But now, what about if we eliminate? In fact, we say, hey, you know, I don't really want this derivative form, and we are going to eliminate the derivative form by now suppressing that mass that in fact should not be there, and finding an equivalent system that has only one mass on the left hand side. See? So this system now is equivalent to this or this one. They should have the same effect, should have the same, you may say, the physical consequence of the behavior of this has to be the same.
So basically, you don't know.
So in this case, we have an equivalent system that has only one mass. And when you do the causal assignment, everything is fine. And this model can be processed fine. But now you say, what does it mean to have this equivalent mass at the point A? We have lumped I-30 with I-27. What is the mathematical principle behind this? The idea is that the equivalent system must have the same kinetic energy. So one half of the mass times b squared should be one half of the mass equivalent times the velocity of A. Do you see what I mean? In other words, at A, there has to be some equivalent to this. So the ratio using the lever ratio here, velocity of A, is A over B times the velocity of B. And if the mass B is placed at A, what's the equivalent mass? The mass equivalent would be B over A times the square times MB. That would be the equivalent mass. So if you do you see how we obtain this thing? We started over here on the where you have, this is the energy equivalence in here. So you could from here solve for the mass equivalent and combine it with this equation, and then you'll obtain this. Okay. The total mass at A then becomes the original one. This is I-27. Now what we are saying is the I-27 is, this is equal to the original MA plus the mass equivalent. Yeah. And by adding these two, we have done what many authors do, combine the inertia elements into one. Yeah. You see, if we put the first one in the CAMG software, do you see what's happening? The computer flags us down. This is derivative form. Yeah. And then if we have the equations of motion in derivative form, we should study it in a simple example as to what the effect of this is. So if we take the top part of the beam and we study it like this, let's take a look at the result of the differential equations. So just for the sake of example, we take the top of the beam and we write this part that has the normal I element and the derivative element over here. We know how to derive the individual equations of the system. So if we write the differential equations of this bone graft model, you're going to see two significant different equations that we would not have obtained otherwise. That is that E sub 6 is dp6 and P sub 6 is I6 times F6. This thing here, do you see what's happening here? This is the derivative on the right hand side of the differential equations, yeah? Okay. You see the other one is over here. This one is fine, and so is this. In fact, this corresponds to this, and to that. So three equations. So, and the other one is of course here, dp1. See, so this is 1, this is 2, and this is 3 equations. And then we have this lonely one that has the derivative one. So what to do with this? What do we do with this? So in order to solve this dilemma, we know that we have this implicit equation. If you put them in the Cauchy form, the first three equations are fine, and look at the fourth one. It has this derivative on the right hand side. Yeah? So this is what we need to solve. This is the Cauchy form of the equation. Now, if we look at the derivation of the state space form of the example in here, we want to find out the explicit form like the one we have expressed here on the right hand side. We need this. We need this. This is state space. This is the normal state space form. This is what we want. So the question is, when we have this kind of derivative form, what can we do to obtain this normal equations form? Let's go back to the Kemp-generated implicit Cauchy form symbolic equations in this. If you process this into the CAMG software, the program is telling you there is derivative causality. See here, see what it says in here? It's talking about this, okay? But if you insist in generating the equations, CAMG is not going to object, and it will produce the implicit set of equations. And then it leaves it up to you to solve those implicit set of equations. And the way we do it is this. See, and here on the right hand side, if you say dp1, you have this dp6 times this, and you see dp6 is dp1. So this is what we will, the first three equations, what we would get out of the CAMG solver. So now, a discussion of this follows. If you look at this forming here, that is on my right hand side over here, you look at this form, it's as if we have another set of matrices on the right hand side, which I call them E. The E matrix multiplies derivatives. So we have the normal ones plus this. And now we have to determine the value of that, the value of this in terms of the normal variables. That's the dependency, you see. So if you do that, you see you could have the original plus now this, because I'm writing for a whole set of equations, these are several equations, and so are these. Okay, so x dot will have to be equal to ax plus bu plus e times f times x dot. Yeah? But you see in here x dot, if now we solve it, you see you have x dot over here and you have the x dot over here. So let's move this term to the left like that, as I have done it over here, and we continue the solution. See? What I suggest is that you see um, from here, to solve explicitly for the states variable, for the derivatives, we will have to invert this matrix and multiply by both sides, and we'll obtain this equation that you see on the right hand side over here. This thing here has x and then it has u, the state variables and the inputs. But isn't that is what we want? That's what we want, the derivatives in terms of the, so we have discovered a new set of equations. See here, this one right here becomes a new, and this other one here will become this like that, including this, same thing here, including this was b new. And so this is what you will see, a new plus b new plus cx plus d new, a and b new. So this is the heart of this paper, because I am presenting the fact that even if you have derivative form, you can still solve it by solving it as a dependent variable, combining it with the others, with the normal ones, and coming up with this new A and B matrix. So new A and B matrix would be the solution for derivative form that CAMG will offer us. start generated, and then you have, if you have it in CAMG here, you will produce these equations that you see on the right hand side over here. Yeah, we will produce the new A. Yeah, this would be the A new, and then we will produce the B new. See, so this is system without derivative causality, and this is system with derivative causality. You could begin to see very clearly that the introduction of derivative form complicated our expressions. Yeah, and that although this we solve this by using the derivative form, the expressions for A nu and B nu are more complex. Okay, so in here we have a system without the derivative form, and then we have the system with derivative form. One will produce a simple A matrix, the other one a little bit more complex because of the process we just went through. This is what we had in here, but that's the more complex matrix. This I just wrote it in here for comparison. Okay. What is going to happen is that now if you have a system like this, I deliberately introduce and suppress the damper and the spring over here. And you know what it did? When I put a solid rod in here and I have these two masses, I went even deeper into trouble. But do you see clearly that you shouldn't do this in reality? This really exists, a spring and a damper, but I suppress it, and in doing so, I made the motion of this one dependent on that one. And that's very clear. When you have that rigid beam, rod, one moves, the other one has to follow. There's no two independent masses. But and you put this into CAMG, it would flag you down real quick. Now you have 1, 2, and 3 derivative forms. So we complicated things. Let's say in here now I'm going to do something else. Instead of making one spring, I put 2. Well, that 2 throw me into another derivative form here. So now we have a real trouble. 3 derivative i's, 1 derivative c, 4 elements with derivative form. The method that I have proposed here to solve this holds. See, there it is. If you put it into the CAMG software, you have 1, 2, 3, 4 elements in derivative form. And in here, CAMG will produce these equations, and then you see 1, 2, and 3 on the right-hand side. And then you have this. These are the 4 dependent equations in there. We will have to apply what we said we were going to apply, and then the computer will solve that. But the solution that the computer offers me, once I have done the equivalency, it's like I tripped the system. I just went ahead and clip all the unnecessary elements. And the element on the right hand side became the one on the left. The element on the right hand side is the result of having combined the elements on the left hand side. Okay, and solve with what we have solved. So this element, this A nu and B nu, they have meaning. They take physical meaning here. So there it is, the solution for this example in here. A little more complex on the trying to solve this produces a more complex matrix to find this A new and B new, but once it's done, it works. And then finally, the Simulink solution here, you have in the CAMG, you have those dependency. The idea is that CAMG will produce the equations that you see on the left-hand side, and also those equations would be used to produce the block diagrams on the right-hand side. In here, the way I have it is like each equation is one window, okay? And so if you produce that, you will see that we have the derivative form, and we will see that we have all the equations um, in the correct way, because with the A new and B new, that's not a problem. So this is the way we put the Simulink to solve the derivative form. See, this are again continuing with the same example. All right. So in summary, there is hope for finding solutions for derivative form by using the A new and the B new, and those can be also entered into Simulink.